Thank you. Good morning, and I'm very happy to be here. I'd like to do a small survey. How many of you attended the tutorial on Sunday? Wow, that's pretty good. Okay, so it looks like almost everybody here has attended it, even though I just found out that about 2/3 of the attendees were there, the workshop attendees. I don't like this business of having to stay in one place to talk, but I've been told no choice. Let's see. This presentation I've given in slightly different forms in a few places, but this is the first time I'm addressing such a heterogeneous kind of audience. So I'm not a hardware guy. I'm a pure software guy. All the 29 years in IBM, I've done only software work, although a little bit of hardware stuff I've done for the IBM mainframes, so-called coupling facility, parallel sysplex, and all that. But I definitely don't qualify to talk about the real hardware aspects, but I still have a few slides here that are like the basics relating to PCM and such. It might still be worthwhile showing those, but I thought there may be more people here who didn't attend the tutorial, for whom it might be even more beneficial. But I'd like to acknowledge a whole bunch of colleagues at IBM that have been working on various aspects of PCM, in particular on the hardware side, the computer architecture side, and the software aspects, as well as the storage software side. Work is spread out across IBM in Zurich, Watson, and Almaden, and we have a representative from Zurich also here, in addition to the two that you heard from during the tutorial. And then there are two of us from Almaden. There was a poster yesterday from one of us. And there are these references I've given here, but then in the tutorial, I guess you'll see a lot more references, and so these may not be that valuable. Although the tutorial that's there by Rich Freitas, he has given it in a few places relating to PCM at the more traditional kind of database-style conferences like SIGMOD and such, as well as at FAST. So you may find those also useful. Of course, we are using SCM as a more generalized way of referring to the kinds of memories that various people have talked about at this workshop. And these are intended to fuzzy the difference between main memory and disk. They fall somewhere in between, and there's a lot of hope riding on these things solving some of the major problems that people have had with Flash, and there have been lots of presentations, and there'll be more today relating to what's wrong with Flash and various approaches to fixing those. It's believed that the price of SCM would be more like disk by 2020 and so on. There's a lot of hype in some cases reality relating to these things. And as I said during the tutorial, if you read EE Times, you don't see as much of hope compared to what you might be hearing in fora like here. There are lots of skeptics on EE Times that are commenting on whether some of the claims that are being made about how good PCM in particular would be will turn out to be true or not. And so I strongly recommend that some of the researcher types also pay attention to such industry rags and see what's being talked about there, about even availability of the chips and when they are supposed to have become available and when they are really becoming available and things like that. Again, some more information on what the difference is between disk kind of storage versus memory, and where PCM fits in this spectrum. IBM has been concentrating more on PCM with respect to the amount of resources that are being devoted. Of course, we've had in Almaden Stuart Parkin and his people working on racetrack memory and things like that. But in terms of broad-based work across the whole spectrum, top to bottom, it's PCM that's receiving a lot of focus. By the way, I should also warn you that nothing that I say should be taken as IBM's opinion and so on. This is all my personal opinion, and things may or may not turn out the way I might be imagining things would be coming out. We've heard enough, so I think one thing to point out is that I don't think the tutorial said so much about availability of chips and such. There's been a lot of discussion for a while about Samsung and Numonyx releasing chips with certain capacity. Some of it has come out, some of it hasn't come out as was expected. There are other people here who could comment on why that's the case, people from those companies. And also in terms of density, there are again, discussions about the manufacturability of some of these chips. You might get some small quantities, but in terms of production quantity, there's still concern about how soon these things might come out and at the price points that people thought they would come out. So there's some more details here. There are lots of companies obviously working on these things, and so for instance, Numonyx had said 1 gigabit chip was to be available last year, but it looks like it might become available only this year. Samsung is about to report on a 1 gigabit chip at ISSCC later this month, or I don't know exactly when it is. Sometime in March is all I know. And of course, more recently, I'm sure you guys are aware that Numonyx was acquired by Micron. So that maybe, because of some of these sorts of things, there may be greater focus because deeper pockets and so on might come into play. There are lots of IT players, as you've heard from HP and various other companies, people that are working on these sorts of things. So you can draw a matrix like this and show, where PCM fits and SCM in general, and how, non-volatility is not the same as persistence, because persistence is supposed to refer to the fact that, beyond a certain time when even your chip gives up, you still want this data to be accessible, and so that might, as a result, force you to have redundant copies of the data and things like that. So this is the difference again between, flash being used in consumer-grade environments to being used in a enterprise kind of environment, which requires that you do all this wear leveling and things like that. And the same sort of thing would have to be worried about in the context of PCM also. And that's what is going to make the adoption of PCM kind of technology in traditional transaction processing kind of applications much harder to accomplish because we can't be as casual as you might be with your photographs getting messed up or your audio recordings getting messed up in your iPod or whatever when the flash chip goes kaput. And so that's what this picture is trying to show. Again, I don't think I should spend time on this at all, except to point out that there are different kinds of storage class memories that people are working on. And what we have chosen to focus on, as I said before, is on PCM. So the SCM is fitting somewhere in between RAM and disk. As I remarked during the tutorial, nobody can, claim that just because this is going to act like disk or act like memory, either of those things would disappear in due course of time. As I said before, even now tape is still being worked on and new developments are taking place. And so just like relational didn't completely replace hierarchical database systems, it'll still be the case that these other media will be around for a long time to come. And also user expectations with respect to these sorts of things keep changing. And so even if you have large quantities available, the database sizes still keep growing. And so in certain environments, you may find that the database fits in memory, but there are lots of other environments where that's not true. In that sense, even if SCM becomes very cheap and all that, it might not completely replace disk as the persistent store. And there are other aspects that I don't think have been talked about unless I missed some talks where they discuss topics like, even if this memory is persistent and you attach it too close to your CPU, if the CPU goes bad, if you can't get access to that memory unless you bring that CPU back to life or replace that CPU with a new CPU, that persistence is not terribly useful because we want high availability, right? So for such reasons, just like disks used to be dual-tailed, where you are able to access the same disk from two different systems, like Tandem and such companies did that long, long ago. Even in the context of this PCM kind of persistent chip, you need to worry about that aspect. And for that reason, in fact, there was a piece of work done at HP where they made the chip be off-board so that it could have multiple paths to it. So even if the primary path becomes unavailable because the primary CPU goes bad or the power goes away, you could still get at that chip's contents through a secondary path. So those aspects are other things that you need to worry about. It may be cool to have it on the same chip as the CPU and all that, but if that means that it's an all or nothing situation, if one part of that chip goes bad, then you can't do anything else with the rest of the chip. That's not terribly useful, or it doesn't satisfy the needs of a transaction processing kind of high availability environment. Okay, so the other point that's been made, I'm not sure if that's been emphasized enough, is I've been told by the hardware type people that depending on the kind of usage you are going to put the chip to, you may make it differently. Meaning, if you're going to use the PCM as a disk replacement, just like a flash SSD, they might build it in a different way than if you were going to think of it as a DRAM replacement or a supplement to the DRAM. Even the density and all that apparently can be done differently. And so that needs to be kept in mind, and that's what this is trying to say, that if you're going to use it in a memory kind of context, speed would be a bigger factor than if you're going to use it like a disk replacement. And also the synchronous versus asynchronous way of accessing. Today, flash is pretty much being treated like disk, and so all the access to flash are happening asynchronously from a scheduling perspective and all that. The process that issues the call gets descheduled. Whereas when you treat PCM as memory, then it's like accessing DRAM, so the CPU is going to be twiddling its thumb while you are doing your PCM operation. And so those things also make a difference in terms of the system architecture and the performance and all the other things associated with it, even failure handling and such. This picture is just trying to show how the speed differences between these different types of data storage media can be related to in terms of real life times. If you equate 1 nanosecond to a second in real life, accessing tape becomes like a century kind of time frame. And you can see with the SCM, it's more like an hour or so. Whereas with DRAM, it's more like 100 seconds in real life. So for some people, visualizing it this way makes it a little more relatable. These are some of the numbers my friend had shown in his tutorial. This is, I believe, Rich Freitas' slide. So this is where I meant, this is what I meant when I said earlier, PCM-S versus PCM-M, S is being like storage and M being like memory. I'm being told that even the effective cell size could be different between the two, like 0.5 F squared versus 2F squared. And even the read latency, there could be differences coming from that. Write latency, of course, is pretty much the same in both cases. Okay. So now come the discussions relating to how you hook up an SCM chip into the computer architecture. If you attach it to the memory controller, as shown here, this will be pretty much like the way you access DRAM. But you could still attach it to an I/O controller by itself or through a storage controller. And what you do with these things, as I said a few minutes ago, will be like, in this case, synchronous access, and that's more like the memory kind of thing. That's from this picture that I had before. That's this one, this red oval, versus the other one, which is the purple colored oval, which is this, where you access it through this I/O controller, and hence it becomes an asynchronous access. So typically over here, you could use it as a supplement to DRAM or as a replacement for DRAM. There was a little bit of discussion about this yesterday, exactly how you expose these things. So one possibility is when you're doing memory allocation, extent-based allocation, the operating system could be told, I want memory in my virtual address space that's backed by DRAM, or I want it to be backed by PCM. So we did a prototype in Almaden where we used some software that had been developed previously for usage in the context of memory in the disk controller, persistent memory that was in the disk controller. So it was a Linux-based software where the extent allocation mechanism was enhanced for you to, as the requester, specify what kind of memory you wanted. And so the logging prototype that we did with SolidDB, the in-memory DBMS that IBM acquired, we made that one make use of a persistent memory-backed virtual memory segment for storing the database log. Okay. The other possibility, of course, that's been discussed quite a bit is adding one more level to your storage hierarchy and making PCM be in between DRAM and the more traditional disk storage. Then all this question about whether it's transparent or non-transparent to the higher levels comes in. At what level in the storage, in the software stack, software/hardware stack, do you make this piece of hardware be known to exist? And should the rest of the things be aware or unaware, then becomes an issue. In the case of asynchronous, of course, by the way, this stuff over here could be one where only the operating system may be aware of the fact that there is something called PCM, and it might use it for only certain restricted purposes. Whereas when you use it in this fashion, more like disk, you might use the PCM more as a paging store, as I believe some of the vendors have talked about doing with even Flash. So it could be just a faster disk storage, and it's used only by the operating system and not necessarily by application software. Okay. So this one is saying how over time you are going from essentially a 3-level hierarchy to a 4-level hierarchy. So here you have DRAM, disk, and tape, whereas here you have DRAM, storage class memory, disk, and tape. And so this is all stuff that I'm pretty sure you guys are aware of. But the thing that you might not have thought about enough is, in the case where you do hide the fact that SCM is there from the higher levels of software, but it's known to the lower levels, the question is, at what point should stuff get moved around between DRAM versus SCM versus disk? And so this is where the kind of software that does automatic migration of data based on access patterns and usage comes into play. Just like you have in a traditional DBMS, the buffer manager, which keeps track of access patterns and figures out when to kick out something from the buffer pool, when to bring it in, and how long to keep it in the buffer pool with LRU or MRU kind of management algorithms being used. Similar things will come into play here. In Watson Research, there's a database group that's working on these sorts of things. They've been primarily concentrating on Flash, but the same sorts of ideas they're going to be extending to deal with PCM. And so the notion of hot data and cold data, and how over time even what's hot might become cold and what has been cold might become hot, and all that comes into picture. And so the time duration during which you track these things and how soon you react and all that are various things that people are doing research on. And what the granularity of movement is, whether you do object level tracking or you do page level tracking or record level and all that, or various options available, and they have different implications on database systems, internal architecture, and things like that. What else? Let me see. I think the rest of it is fairly obvious stuff. And of course, one of the things that's been talked about a great deal in terms of leveraging the persistence characteristic of these kinds of memories is trying to improve the reboot time. If you have logged out of your machine and you want to be able to boot much faster than what it takes these days to do it, if it's a disk-based way of rebooting, then the use of something like SCM could be very valuable. And the same thing, of course, applies to when you are, what is it called that? Where you dump the memory contents to hibernation. Hibernation also could be improved if you have this very fast access kind of memory available, rather than having to wait for rotating platters and all that to do their job of bringing the stuff into memory. Okay, the other thing that's also possible is in the case of traditional database systems, we have had the notion of different buffer pools being there even in a single instance of a DBMS, and trying to give differential treatment to data of different priorities and such. For example, the indexes may be put into one kind of buffer pool versus the data pages are put into another kind of buffer pool, and you may allocate more storage for the index buffer pool compared to the data buffer pool and things like that. Because that's a very high-level way of dealing with more frequently accessed data versus less frequently accessed data. The same sort of thing could also come into play when you have data that's expected to be accessible at, with very low latency. We've recently dealt with a Wall Street firm which wanted to have, this was all a bit too much of futuristic stuff, but they wanted to have petabyte of data in memory, in DRAM. They wanted to have tens of millions of transactions being executed per second, where a transaction was a simple object put or get with a primary key. They separately said you can have metadata that's treated more like a traditional relational one with queries involving predicates on something other than the primary key of the objects. And they wanted sub-millisecond response time. And so petabyte of data in real memory, not even PCM or anything, but DRAM, 10 million transactions per second update, 50 million transactions per second read. Those are the simple 1,000 byte or so object put and get. And then an unspecified query workload, which will involve columns that are metadata columns. And for those, they didn't have any stringent response time requirements and such. And so this is the sort of thing that some of these high-end Wall Street firms are trying to accomplish. But the idea of keeping a lot of data in main memory has been the vogue in the case of the Web 2.0 kind of companies. Facebook, Twitter, all these guys are now pushing the limit, and hence all the work that's gone on with key value stores and such, this so-called NoSQL movement. Some people interpret it as NoSQL means no relational databases. Some other people say it's not only SQL, SQL plus non-SQL. And that's an area where even at Stanford, for example, there's a project, what is it called? Something RAM. John Osterhoff's project. RAM Cloud, thank you. Yeah, RAM Cloud. So he is, of course, trying to do this in the context of just DRAM. And he's trying to make accessing memory across the cluster be ultra efficient compared to the traditional ways in which a NUMA kind of architecture might let you access it. And even in the case of IBM, the so-called P7IH machine, which is the PERC system that was developed at Watson and our Poughkeepsie kind of places with a lot of government funding originally, NSA and such, that is a super duper kind of machine. It's like a follow-on, if you like, to the Blue Gene type of machine architectures, where the maximum delay you get compared to, delay in accessing remote memory. It's a cluster with, you can have 2,000 or more kind of nodes, where each node consists of 32 cores, half a terabyte of memory in each node, up to 32 cores within a node. 3 times is the maximum delay you'll incur when you try to access the memory that's in a remote core, a remote node. From one node, if you try to access the memory in another node. And that's considered much, much better than what you could get with a sequent kind of NUMA architecture machine. Okay, so there are people who are now exploring all those things in the context of DRAM, as well as in projects like ours, trying to go and look at what the implications would be if instead of DRAM you're going to use, or in addition to DRAM, you're going to use something like PCM. So this picture just tries to show how across the whole stack you might try to leverage something like PCM or SCM, whatever you want to call these things. So it could start all the way from the bottom over here, or going to the kernel, where over here you might benefit from SCM for the purpose of paging, as I said before, or as you have heard from references being made to the work by the Microsoft guys in SOSP 2009, which had to do with a newly designed file system that's intended to let you make use of PCM as the storage medium rather than disk. They made certain assumptions, and I believe the tutorial talked a little bit about that. They have assumptions about 8-byte atomic read and write capability, and they also have some primitives for you to group a collection of operations as being in one epoch and another set of operations in another epoch, and then they'll guarantee that the second epoch's writes will not happen unless the first epoch's writes have been finished. But within an epoch, the writes might go out of sequence. Some of those sorts of things are being worked on, and I will make references to some of this a little later. And also, there is a lot of expectation slash research kind of work going on with respect to how, in the more traditional environments, if you look at an application server environment, a lot of the data manipulation is done using object-oriented primitives, if you look at Java kind of application environments. But the persistent version of such data is stored in relational systems typically. And so there's always this need for mapping from the object view of the data to the relational view, and the other way around. On storage, you have to go from object to relational. On retrieval, you have to turn the relational back into object. So the hope these days is that maybe if that memory itself is persistent, you don't need to go through this back and forth of conversion from one form to the other, and people that are coding these applications can treat that memory that they are manipulating in the application itself as being persistent memory. This is not too different from, and again, some people are not going back and looking at enough of the old stuff. There's been a lot of this kind of work that's gone on for more than a decade in the context of persistent object programming systems. In fact, there was a reference to Microsoft work, I think, yesterday. I forget now, Stash something. Some of that looked pretty much like what the object store guys did. ODI had worked on single-level store, where they will get into bed with the virtual memory subsystem and mark pages as being in a state where if anybody tries to read or write those pages, there should be an up call, and then locking will be done, logging will be done, and things like that. So some of those sorts of things become very applicable in the context of this type of environment where the memory itself becomes persistent, as opposed to in these other environments where they made you think that you are dealing with recoverable virtual memory, but in fact, that memory itself was not recoverable, but they then backed it with disk. But you didn't have to think about that mapping from virtual memory to disk. Again, this has been done for eons by System 38, followed by AS400, and now it's called I-Series in the IBM world. So single-level store is not at all a novel concept, but some of the work that's now being done with flash as well as PCM or SCM kind of technologies is very much reminiscent of that kind of work. And so it'll be worthwhile for the people that are doing active work in this space to go back and read up on some of that old pieces of work. There used to be even a conference series on this persistent programming language topic. So that's what a lot of this is saying. You know, your key value stores or XML databases or relational databases or object databases could all potentially benefit from having persistent memory and avoid this impedance mismatch, as it's been called, where the application programming has a certain notion of types and such. The persistent store has a different set of such assumptions, namely the relational system or whatever. And then you have to pay the price of constantly converting and reconverting. And so if the memory itself becomes persistent, maybe you can get away from all this. But the problem that will come with all this is that even if the memory is persistent, but the CPU power could go away any time, then you have this nuisance of having to figure out what you are in the process of doing when the power went away and which of your intended updates got actually done and the others didn't get done. So you'll be left with some state of the database that is one where you, unless you kept a lot of bookkeeping stuff around, wouldn't know what the state is. And so there is a much cleaner way in which we do this recovery in a traditional database system where we don't let certain intermediate states of the database that you create while you're manipulating the database in memory, we don't let that state go to disk. We only let, at well-defined points, after we've established certain level of consistency in a database page, we allow the page to migrate to disk. And so that provides certain clean abstraction for you to deal with when you come back after a failure. We assume that the memory contents disappeared, and we are left with only the database state on disk to recover from. Whereas with this persistent memory, you are now in trouble in many ways because at any given point as you are manipulating, control could be taken away, and you are left with whatever state you had created. And so in terms of leaving breadcrumbs around as a way of doing recovery, you might have to leave a lot more breadcrumbs around than in a more traditional database system where the log is written only at certain points in time. And for some of the data manipulation you do, like garbage collection, for example, within a page, when you do garbage collection, we don't necessarily log any of the changes we make because conceptually the state of the page hasn't changed. Physically, the page has changed, but the data content-wise, it hasn't changed when you do garbage collection and move free space around within a page. And so those sorts of optimizations that we have in a traditional DBMS, we need to rethink when we operate on memory that can make every bit twiddling become potentially persistent. And you could lose control of the execution at any given time because the CPU may disappear on you at any given time. What else? Let's see. I think that pretty much covers everything here because there's some of this discussion here about single level store and memory mapping, and there was a reference to mmap yesterday in one of the talks in the other building, for example. A lot of that has been worked on quite a bit by the DBMS kind of vendors. And they didn't succeed as much as they had hoped at that time to succeed. And there were a lot of other implications that came from, for instance, in object store initially, because of the way they were leveraging the virtual memory subsystem, they were restricted to page level locking. They couldn't do finer than page level locking because they relied on this upcall to let them know when the first update to a page was happening. And after that, they turned off that upcall. And so subsequently, they couldn't tell which bytes in the page got modified. And logging also was very physical in nature, not logical and things like that. So there are many things that one could talk about, and depending on the interest, we can go into questions questions here or outside of the room. So I'm going to take a few use cases and then use the database context as a way of discussing some of the issues and so on. So by the way, this talk doesn't really give you any great solutions or anything, unlike what Shuki did. This is more a way to make you think about what the issues are and raise a lot of questions in your mind than to give you any solid solutions. So we've discussed some of these things. The one that might not be obvious is PCM as extended memory. In the good old days when IBM had 24-bit addressing, and you could have maximum 2 gig of real memory being addressable with 31 real memory addressing. Even when we went to 32-bit virtual addressing, real memory was still restricted to 31-bit addressing. 2 gig was the maximum. But then the memory became bigger than 2 gig, the physical memory. So the question was how to leverage that additional memory that was available. So that's when IBM introduced this notion of access registers, extended storage, and so on. So the way that worked was you could use special instructions to get at this other kind of memory beyond 2 gig. But the rest of the software, which it would have taken too much effort to go modify it to make use of access registers, was still operating only with 2 gig as the maximum storage size. And so what you had to do was move in and out of this extended storage, the pages, before you could manipulate them in your 2 gig address space. So essentially, this is like the good old days swapping thing, right? And so that's one way in which you could treat this PCM, for instance. Your existing application that operate off of DRAM could still be doing what they've been doing forever, but you could put the data that gets booted out of DRAM into PCM and drag it back into DRAM when accesses are made to those parts of the data that are not in DRAM. And so this is another way in which we have leveraged, for instance, in the context of our version of shared disks support compared to Oracle, for instance. We have this memory called the coupling facility, which is page addressable store that's shared across a cluster of machines. But the individual database instances in the sharing machines cannot directly manipulate the data in that coupling facility. You have to drag the data from there into the regular buffer pool before you're able to operate on them in a byte-oriented fashion. The same sort of approach could be adopted for leveraging PCM. Okay, so this just tells you a little bit about the project we have had for a while in Almaden, where we were trying to understand the architectural implications of storage class memory. In the case of Watson, they've been paying attention more to flash, and in due course of time, they'll also be focusing on PCM. These are the guys under the group headed by Bhatta. We are investigating, of course, the whole software stack, but pretty much in the context of database systems. But there are other people in Watson, John Caridis' group, and I guess Mohan is in that same group, right? Yeah. No? Yeah, okay. Who are all exploring the architectural implications in terms of the operating system and the layers between that and the hardware. How exactly you expose the memory and things like that. And then there are other people in Almaden on the storage software side who are looking at the aspects of how to leverage this kind of memory in the context of the file system and things like that. We, of course, are very much aware of all the things that are going on in the open source community, especially in the context of Web 2.0 type environments like Facebook, Twitter, and such, where large amounts of DRAM, as I mentioned before, have been leveraged. And projects like the RAM Cloud are also trying to make a difference. And so we decided instead of trying to work with an existing relational DBMS which has been designed for a disk-based persistence environment, or even for that matter in-memory database systems like SolidDB that IBM acquired, or times 10 that Oracle acquired, which were designed for a non-persistent in-memory environment, maybe it's better to focus our efforts by looking at a key value store, because we don't have to worry about all the full-blown SQL-related complications in this context, since it's an exploratory project, and try and see how we could leverage a PCM kind of persistent memory. And we felt by doing this, we could also bring some more value to the Memcached kind of environment, an open source key value store, because they've been used more in the Web 2.0 community rather than a more traditional transactional kind of environment, where because you and I get to do a lot of things for free, we can't complain too much if they lose our data and things like that. But the same thing can't be true if these things are going to be adopted in the kind of Wall Street type of environment that I mentioned before, with all their fancy availability requirements and performance requirements and such. And wherever possible, we thought we'll benefit from the other kinds of software that we have around in order to reduce the development cost and things like that. For instance, picking up a lock manager from our SolidDB in-memory DBMS. Since I can't give you the details, we haven't gone through our patenting and all that, I'll just briefly tell you what's going on with these boxes here without the details being shown there. Essentially, what we said was, let's take something like Memcached and make it use PCM as the persistence medium rather than traditional disk as the persistent medium. Then the question was, what should we be doing? What is the role of DRAM versus PCM in this environment? So the way we have gone about doing this, we have figured out that there are certain data structures which, for instance, like this box, will reside only in DRAM. This could be something like, for instance, a log table, right? If the system were to crash, if you're not worrying about distributed transactions and such, it's okay if the logs disappear, because on restart, we'll do recovery and we can figure out what was in progress and all that, and we don't need the lock information to be available for that. But there are other data structures which will only be on PCM. So whenever we manipulate the data, for instance, we could choose to have the data only in PCM and directly manipulate it in PCM. And then there are these other data structures where we have copies both in DRAM and in PCM. So now it's a question of whether these two copies are kept in sync lockstep, or do you have one version being more up to date than the other version. So for instance, some metadata, initially we might manipulate only in DRAM. And at certain well-defined points, then we will move it to disk. This is, to PCM in this case. This is no different from in a traditional database system. We write the log records initially in memory. There are log buffers in volatile memory. And then at transaction commit time, we would force the log, thereby making it persistent and moving it to disk. In this case, we will move it to PCM. And then there are also other pieces of metadata relating to storage management and such, which initially we might only do the manipulation of in DRAM, and then at certain defined points like commit time, we will move it to PCM. So what are some of the implications of these sorts of usage? So one possibility, as I briefly mentioned earlier on, is that you could just say, I will leave the rest of my DBMS all as it is today, in the case of, let's say, SolidDB, but I'll just make the logging component alone make use of PCM as the persistent log medium rather than disk. And even when you choose to do this, there are still options available. Whether the log buffers themselves will be only on PCM, or you still treat it like traditional situation where the log buffers are in DRAM, and the time when you commit a transaction, instead of moving the log records of that transaction to disk, you instead write it to PCM. The former is going to be more expensive because you are replacing a DRAM write with a PCM write on every log write. So that could add path length. And when I say DRAM write, many people don't think of the fact that it's not actually a DRAM write. It's a write into L1 cache. So comparing DRAM versus PCM performance is not always the right thing to do, because if a write to PCM is going to be assumed to have completed the minute the store instruction finishes, then you can't benefit from any of these intermediate levels of caches. So under those conditions, you really have to compare L1 write speed versus PCM write speed. And that's even worse than the normal comparison that people make between DRAM write versus PCM write. That's good. It tells me I have 10 minutes left. Right? Or how much time do I have? 10 minutes, okay. So the other problem that, as I mentioned at one point earlier, is if this PCM is attached to the processor in the same chip, for instance, you may wind up getting less availability using PCM as your persistent medium than if you had to use disk. Because in the case of disk, the disk may be accessible from another node, right? So when the primary node fails, you could bring up the DBMS on the secondary node or the backup node. It could be a hot standby, or it could even be a cold standby. You could bring it up and that guy could go access that disk and do the recovery. But if you have now shoved this PCM chip onto the same board or whatever, and you don't have an alternate path to that memory, then your availability could suffer. So those are some of the architectural implications that you need to keep in mind. What happened? I see. Okay, so the other question that comes up in this context is, should you replace your existing DRAM buffer pool with a PCM-based buffer pool, or should it augment an existing buffer pool? And that's where I said you could even think of having side-by-side both the DRAM kind of memory as well as a PCM-style memory. And you could choose to put the more frequently accessed data or the data with the greater response time requirements into the PCM buffer pool, and the slower thing could be put into DRAM buffer pool. But here again, the issue is the writes into such a PCM buffer pool will suffer because of the greater time it takes to do the write. And that could have implications on, even if response time is not a consideration, humans can't tell the difference between 100 millisecond versus 200 millisecond response time. It could have implications on lock hold times. So if concurrency is an issue in your system, there are some hotspots, then it's that will have a greater effect than human perceptible kind of response time differences. And so here again, you need to have clear-cut ideas about what it means for this memory to be persistent. When is the persistence guarantee said to be true? Is it right after your store instruction finishes, or you have some kind of a sync call only after which? And so the Microsoft work assumed that it's not after every store that the data is persistent, only at certain well-defined points when you issue something like a commit that it becomes persistent. And so in that sense, you can't anymore make any assumptions about this persistence in the same sense that somebody else might be thinking when they assume a store, once it finishes, it's persistent. And that has to do with whether any of these intermediate levels of caches can be leveraged or not. And there was this piece of work, believe it or not, done in 1989 by the MCC guys in Austin, where they assumed you had a small amount of persistent store available in your DBMS, but the rest of the memory was non-volatile memory, and they used that in a very specialized way. Instead of writing stuff from volatile memory to disk, they would write it into this safe RAM, as they called it. And when a system fails, they assumed there was enough power available or whatever for the content of that safe RAM to be dumped to disk. So as far as restart recovery was concerned in their DBMS, it was business as usual, because at restart recovery time, you still dealt with only the version of the database on disk and did all your recovery from there. So this was an attempt on their part to make the write to disk become faster by leveraging this kind of memory and not do as many writes to the real disk, instead do the writes to this safe RAM. So that was just a very simple-minded effort that was done, but it was done quite a long time ago, and not too many people actually are aware of this paper. It was, I think it says it, right? Oh, it was in VLDB 1989, by the way. It doesn't say it here. The other one is, should you assume, in the case of an in-memory DBMS kind of environment, that the whole database fits in memory, or do you still want to be fits in persistent memory, or do you want to assume that it doesn't fit in memory, and so you still need to deal with having to move in and out of this persistent memory portions of the database that are fully resident on disk? And also in this context, the question that then comes up is, should you take an existing in-memory DBMS that was designed for a volatile memory environment and tinker with it in order to make it leverage persistent memory, or should you start from scratch and build some brand new kind of code with new ideas and such to, from the ground up, leverage persistent memory? So this is where some of the so-called benefits of persistence can come back to haunt you, and there were some references made in the tutorial to this topic, which is one of the good things about having the separation between volatile memory and persistent disk today in database systems and such is that there are only well-defined points, as I said before, when we let data migrate from the volatile memory to persistent store, and we do some amount of sanity checking at that point in order to make sure that what we are about to make persistent doesn't have any inconsistency and all that. So we do a certain amount of consistency checking of the page contents before we let it be written to disk. And we still have to, of course, worry about partial write of that disk page in case there is a failure which results in not all the page content making it to disk. And so we have some certain amount of logic in our systems to detect a write that was only partial, because the hardware doesn't guarantee across sectors the detection of a partial write, and so we in the software have to worry about that. But the additional thing that you could get into trouble with all of your memory becoming persistent is that any bug you have in your code, whether it's the application code or even the DBMS code, could now wind up going and corrupting the persistent state of the database. So there's a lot more stuff that you need to think about in this context if you want to deal with these sorts of situations. And I've already mentioned this last point, whether or not you are doing a write through the L1, L2 kind of cache. You may benefit still from those caches with respect to reads, but for the writes, it's a question of semantics that you assume about the persistence that will determine whether or not you get the benefit of the L1 and L2. Then the other thing that many people have talked about or very casually referred to in this context is, oh, since the whole database is persistent, I don't need to do traditional logging that DBMSs have been doing forever. Some of these people think, in a transactional system, it's an all or nothing property, that a transaction commits or a transaction aborts and end of story. That's not quite true. We have this so-called partial rollback, statement level atomicity, as it's called in SQL. A portion of a transaction may be rolled back, and still the transaction may make forward progress and then commit. So in order for this partial rollback to be done, typically you need to have a log, whether it's an explicit log or an implicit log, it doesn't matter. So versioning still doesn't get away from the need for doing something like this. People also think, shadow paging solves all the world's problems. That's not true. I mean, sometimes the way the shadow paging is done by people, they are only supporting either a commit or an abort and no partial rollback. As long as you have to do partial rollback, you are back into having to have some form of log. And the other problem that people don't always pay attention to is dealing with failures where even the memory gets completely wiped out, right? Because something falls on it and it breaks, or the whole building collapses. So disaster situations and such. So for any number of such reasons, you cannot but have to deal with logging in the more traditional sense, possibly with some variations, but still, you can't just wave your hand and say there's no need for logging in this context. And so some of the research work is simple-minded in that sense, and so that needs to be dealt with in a more comprehensive fashion. I think I've already mentioned these points, so I won't dwell on this, except to say that the endurance problem is something that also is a reason for worrying about logging, because the memory, even if the building is intact, but the memory no longer works, and you had some valuable data there, how are you going to recover from that? So either you have to do replication in the main line, or you have to periodically do backup of that memory content, and then if the memory gets corrupted, you have to somehow bring the last backed up version of that memory's content up to date as of the time of the memory's failure. And in order to do that roll forward, you will still need log records or some way of redoing the transactions that executed in the meantime between the last backup and now. I think I've already covered this, so I shall ignore this. High availability, again, I think I've covered this. So even the locking, for example, that I said we could just keep in volatile memory, that's not quite true if you're in a high availability environment and you have distributed transactions and such. Even the locks might have to be made persistent, and that's what we do in the case of, for instance, that parallel sysplex coupling facility environment that I mentioned, where in a clustered environment, DB2 is running on many different mainframe machines. And this is now true of our Linux, Unix, Windows version of DB2 also. And then if one of the nodes fails, Oracle has a harder time dealing with such failures than what we are able to do, because we have this persistent memory in the form of this coupling facility where the dead machine's write type locks are tracked. And so as soon as the failure is noticed, we can continue to let other nodes, transactions, keep doing their work, and new locks can be granted, because we know what are the locks that are needed to protect this dead node's updates. While that dead node's recovery is going on, we'll still be able to handle the processing of transactions in the other nodes. So such things would also be relevant in this context if we want to permit new transaction activity while recovery is in progress when a node has failed and you are bringing back some alternate node or that same node to do the recovery. I've mentioned some of this also, whether or not you should start from scratch and redesign a brand new DBMS. I'm almost there. So there's all this work that's gone on in the context of different products and such, especially in an application server environment where people have traditionally had caching being done in the application server environment, typically in-memory caching, and there'll be a back-end node where you will have traditional database systems persistently storing the data. Even in these sorts of contexts, it will make sense to try to leverage the persistent memory and provide much better performance with all the high availability and high response time requirements that I mentioned, like the sub-millisecond response time and things like that. One of the things that we all have been trying to get hold of, if you looked at Flash, the thing that made it become very successful in terms of market penetration and all that were these consumer kind of environments, right? Digital cameras, personal music players, and so on. And there, the requirements were not as stringent in terms of reliability and such. Whereas for PCM, if you're going to think of it more as a DRAM replacement, and you're now trying to get into the more enterprise kind of environments, it's still not clear what the killer applications are. And until we as a community figure out that, it's going to be that much harder to see the kind of exponential kind of takeoff that happened with flash memories. And in the context of research community, of course, there's a lot of papers coming out now that have to do with SCM style memory, although bulk of the papers still are more on flash. And since I gave this talk last year at the VLDB conference's associated workshop on transaction processing council, I mentioned the fact that maybe the TPC guys should start thinking about potentially a benchmark that is focused on this kind of memory environment. I think I'll stop here. If you have any questions. Yeah. Okay. Harumi's question is, what's the difference between write-ahead logging in a traditional context versus here? And that's the point I was hinting at earlier, that if you're going to make every bit twiddling become persistent, or it is going to become persistent whether you like it or not because you're operating in a PCM environment, effectively the logs would have to be written before you modify every piece of data, and hence the log also should be made persistent. So in effect, every update is a persistent update, and so the write-ahead logging rule will say that, hence, before you do that update, you would have to write the log, and by the way, you have to make that log also persistent right then. And so in that sense, it's not a good story, because, I mean, effectively, you are now having so many slow synchronous writes of the log as well as the data. And so this is why, you know, I have had a lot of sleepless nights thinking about, is this a good thing or is it not such a great thing, this persistent memory that's byte addressable and I'm directly manipulating it as the transaction does its inline operations. And so this is one of the reasons why I said during the tutorial, the jury is still out on PCM, at least in the context of the sorts of things that I'm intimately familiar with, the transaction processing kind of environment. Yeah.
I have two questions. So first question, there are other types of SCMs. By focusing on your talk on PCM instead of SCM, are you trying to give us any hint?
No, I mean, as I said at the very beginning, I mean, I don't see the distinction so much in this context. As long as it's persistent, and I also said that in IBM, as far as I know, the maximum amount of resources are being spent on PCM, even though, even in my own lab, Stuart Parkin has been working on racetrack memory and things like that. So no, I don't see at the level of discussion I've given here that anything I've said is really that specific to PCM. This is why it's a bit of a nuisance. I keep using SCM and PCM somewhat interchangeably. But unless somebody else has something to add to that. Mohan, do you have? Oh, okay.
Second question. In the key value store project, are you thinking of log-free data structure? Or?
So far, we haven't. Okay, so since you brought it up, some people asked me offline, and I had also thought about. I wrote a paper, by the way, for this workshop, which was a more general kind of paper, a very short one, effect of recent hardware and architecture trends on database systems or something like that. I talk about transaction memory there. People who don't pay enough attention to the real nitty-gritty, gory details of database systems think, you know, transaction memory is going to solve all the world's problems. But I've spent 30 years on concurrency and recovery, And I'm not convinced that these things will really give the kind of concurrency I need. And hence, I am fairly skeptical about how much of benefit we are going to get from transactional memory in the kind of context that I have done my work in, which is traditional transaction processing systems. With all the gory, complicated protocols that I've cooked up for index concurrency control and such, which go far beyond just byte-oriented locking and latching and such. So that should sort of address this question about even lock-free data structures. In certain very limited spaces, they are good. Even in our log manager, we do that. The TPC benchmark, when you really push it to the limit, is such that the holding a latch while allocating space in the log buffer, because everything has to be sequentially done there, and filling the log record with contents was becoming a bottleneck. So even in System R, believe it or not, 35 years ago, they had come up with a scheme, which the product didn't choose to implement for a long time, where they will do the storage allocation under the latch, but the actual filling of the record content they were doing outside the latch, which meant that if some subsequent log record had to be forced, that guy had to make sure all the previous log records had been fully filled in before he was allowed to force it. But it turned out even doing the storage allocation under the latch was causing enough latch contention when you are trying to have 1 million transactions per second and so on, per minute, that they then used a lock-free synchronization scheme over there. But in a general sense, for all the regular locking, I am fairly skeptical that any of that could work. Just like the object store thing in the end didn't work, just leveraging the operating system for doing that kind of thing, because they were stuck with page locking, then they had to go through all sorts of motions to introduce object-level locking. So Mohan had a question. Right.
That's not the case for SCM.
Right.
Writes are expensive.
Right.
It's more slower. Writes are power hungry. There are only so many writes you can do.
Right.
Will database change in response to the expensive writes?
So I didn't directly address it, but I sort of indirectly addressed it by saying the performance sucks for writes, and especially for that reason, if you're going to do your writes synchronously into PCM, every time the SQL application or whatever does writes, it'll be a problem. Fundamentally, there's not a whole lot you can do, right? I mean, you can't replace a write with a read or some such strange thing, right? So as long as the application is trying to do some changes, the only thing you can hope for is you can try to consolidate the writes. So maybe you can do things like the compilers doing look ahead and such. If you have your transactions fully specified, you could do look ahead and combine two separate writes into a single write so that at least in one instruction you can do the write and so on, if things happen to be close together and such. So clustering of the data that's being manipulated could be one way, clustering meaning physically moving it close together. But the general assumption with transaction processing is that you don't know ahead of time what all will be done as part of a transaction. Of course, if it's a canned transaction, you can know that. But in the most general scenario, we assume that the user issues a begin transaction and then gives one statement at a time. And he wants the response for each statement before he gives you the next statement. So off the top of my head, I can't think of any great thing that can be done, except for postponing a write to the end or something, if that's going to help you somehow by combining a bunch of individual writes into a single write done closely together in time. But even that gets into trouble because, and this was a problem with IMS FastPath, the main memory database system, with respect to holding the locks for a short duration. They said, let me not do inline updates. I'll collect all the updates at the end of the transaction, get the locks, immediately do all the updates, and release the lock. So I don't have to hold the lock from the original time when the update was issued to the end of transaction. But then the consequence was, if you did an update and you did a read of that same object within the same transaction later, you didn't see your own update because it was a deferred update that they were doing, right? So there are semantic problems like that also that come up if you try to reorder things. Of course, you can say, well, I need to know then that there may be some update that is pending to be done, and so I should look into that queue before responding to the read. But then that can also, affect the performance and such. Yeah.
Could you elaborate a bit more on the implications for existing and future benchmarking? You said there's a lot of potentials for getting really high numbers that you discussed.
Yeah, so that's one of the reasons why, I think the transaction processing council guys have to say what is legit, what's not legit, and things like that. The other thing, of course, is that there are benchmarks where people are worrying about not just max transactions per second or dollar per transaction per second, but also energy usage and such, right? So this could have implications even there. Even the spec benchmark, I think there is a energy-related aspect to it. And I believe TPC guys have done it or are about to do something relating to energy too. So the green kind of thing also could play a role over there. But beyond that, from a reliability perspective also, there are implications because as part of the benchmark, they do have a requirement that you have to prove that the data is recoverable and things like that. So that aspect might also get affected by this. And so as part of that, should they worry about the endurance property of that thing being taken care of or not? Anything else? Or are we out of time?
Let's take the rest of the questions offline.
Okay, thank you.